Hi everyone, and welcome to my presentation for Lab 5 Physics 2211. The purpose of this lab is to investigate and model any system of interest to you. For me, I picked the rope swing adventure and used the behind-the-scenes video for reference data. We were also supposed to use GlowScript as a modeling tool as well. I also plotted the energy changes computed in the model, such as kinetic energy, gravitational potential energy, change in spring potential energy, and the change in total energy. For my adventure, I decided to investigate whether the rope swing satisfies the energy principle and observe what the model would look like compared to the original video without the force of drag. The results show us that delta E equals 0 because this is a closed system, and that the computer model is not that accurate and possibly overpredicts the jumper's arc. The physics principles involved in this lab were Newton's second law, spring force, and the work energy principle. Newton's second law is rearranged to find the final velocity and the final position of the system, and the net force was calculated by adding up all the forces acting on the system. These forces were gravitational force and spring force. The spring force was calculated using Hooke's law. Since this is a closed system, the change in energy should be 0. The change in energy is equal to the sum of kinetic energy and the sum of potential energy. The potential energy is made of the gravitational energy, which is found through mg delta y, and the potential energy of the spring, which is 1/2 ks s squared, and the kinetic energy is found by 1/2 m delta v squared. The experiment initialization was as follows. All the data recorded here was provided by the behind-the-scenes video. We had to assume the K for the bungee cord, and it was found through some sources to be around 30,000 Newton meters for a strong bungee cord, and that the average mass of a human male was to be 62 kilograms. The initialization of the code included the mass of the man and the original position vector given. The spring stiffness and the relaxed length of the spring were inserted from the reference data found earlier. The equations for L, L hat, and S were updated to reflect the correct calculations. The system energies were computed by putting the correct formulas into the Python code. In the first loop, Newton's second law was used to update velocity and position of the system. And the spring was also updated by putting in the correct equations for L, L hat, and S. To calculate the various energies, we put the correct formulas for each of the energies, such as kinetic energy, gravitational potential energy, and spring potential energy into the code. We added the forces into the code by inserting the known equations from our physics principles as well. Here is a video of my code running. The blue arrow represents the force of the spring, and the black arrow represents the force of gravity. At the bottom, there are two graphs. There is a change in energy versus time graph and the position time graph. The kinetic energy in the change in energy graph is represented by the blue line, the gravitational potential energy is red, the spring potential energy is green, and the total energy is in yellow, but that will be observed in the next slide. The results for the Python code for the change in energy versus time graph demonstrates the change in the system to be 0 because it was a closed system. This was visualized by the yellow line in the results of the Python code. As kinetic energy increases, the spring potential energy decreases and vice versa, so they cancel out. This is the result of the Python code for the position versus time graph for the computer model. The sinusoidal waves demonstrate simple harmonic motion, which is normal for most oscillations. To answer the first question, yes, the energy principle is satisfied. The sum of all energies acting on the system should be 0. This is a closed system, so no energy should be gained or lost in the system. This was visualized by the yellow line in the results of the Python code. As Ke increases, the spring potential energy decreases and vice versa, so they do cancel out. To answer the second question, drag acts in the opposite direction to relative motion. This results in the jumper's arc to slow down and become smaller in width. The computer model does not represent an accurate arc for the jumper because it does not include air resistance. If we had another model to just put it to, we would have a smaller arc. To answer the third question, since the energy principle is satisfied, the rope swing must have some change in internal energy for the total change in energy to be a constant zero. Thermal energy is an example of a change in internal energy, and thermal energy increases with very fast motions and friction, and this most likely causes a small change in the system. Thank you for listening to my presentation. Have a great day.